So let's now solve this question. Find the eigenvalues and eigenvectors for the following matrix, right? For this matrix, let's just find the eigenvalues and eigenvectors. So let me go to the next page. The matrix was 1, 2, 2, 1, right? Now, as you know that to find the eigenvalues, what we need to do? The step 1 is that we need to solve for this equation. A minus lambda I determinant equal to 0. And how I am getting this equation? Because I already explained that in the earlier lecture, that because we have Ax equal to lambda x, and from here I am having A minus lambda I determinant is also 0, right? Because x is eigenvector which is non-zero, and finally we have this as a determinant 0. Okay. Now let's just solve for this. So determinant of A is this minus lambda I. So if you do lambda I, let me maybe do it for the first sake of example, and then we can directly do it. So this is 1, 2, 2, 1, and then minus what is lambda? Lambda is just a constant, and then identity matrix here, which is 1, 0, 0, 1, and then determinant of this whole thing, right? Determinant of this whole thing. So that's what we want to do, right? Now this is actually equal to 1 minus, see, if you just do 1 minus then lambda, then there will be nothing subtracted from 2, and then 2, and then 1 minus lambda. So basically you only subtract from the diagonal, right? So from the next time onwards we will do it directly. And now we want to find the determinant of this matrix. Okay, so let's just do it. We want to find out the determinant of this matrix. So for the determinant, as you know, like we use the sign which is double bars, right? Okay, so this is the determinant of this matrix. Now you can easily solve this. I mean, determinant is 0, and for this you need to find out the value of lambda. This is 1 minus lambda square minus 4 equal to 0. From here you can say 1 minus lambda square, 1 minus lambda square equal to 4. From here you can say 1 minus lambda is either 2 or minus 2, right? So from here you can say lambda is either minus 1, sorry, lambda is either minus 1, or lambda is 3, or lambda is 3. So there are two values of lambda that is coming out from this equation, which is lambda equal to minus 1 and 3. Now we have two eigenvalues here. So what we need to do? We need to find for the eigenvectors. Let's just find for the eigenvectors now, right? So we have two eigenvalues, minus 1 and 3, and now let's just find eigenvector for minus 1 and then 3. Eigenvector for lambda equal to minus 1, right? Let's just find eigenvector for minus 1. Okay, so let's start with the process. Do you remember how to find the eigenvector for minus 1? We have an equation which is Ax equal to lambda x, and from this equation we said that we can rewrite it as A minus lambda I into x equal to 0, right? Now to solve for this eigenvector, we need to solve for x, which means that we need to solve this homogeneous set of equations. And here the value of lambda is already known. See, the matrix A and the matrix A minus lambda I are completely different matrices, and there is absolutely no relation between A and A minus lambda I. That is what first you have to understand. Okay, so I will actually solve more questions, and I will tell you few things here and there. Don't worry, like I will connect all the dots. But yeah, like I'm just telling you that here this A and A minus lambda I, these are the two different matrices, and these two matrices have absolutely no connection. So this A minus lambda I matrix is different from A, and we need to solve for this set of homogeneous equation to solve for x, right? So now let's just write this A, which was 1, 2, 2, 1, 1, 2, 2, 1, and minus lambda, which means plus 1, right? So it will be 2, it will also be 2. So now you have, okay, now you have 2, 2, 2, 2. Great, no, not an issue. So this is A, this is x, which is, let's suppose, x1, x2, and then this is 0. So this is A minus lambda I, this one is A minus lambda I. Let me quickly confirm. 1 minus lambda, 2, 2, 1 minus lambda, right? So 1 minus lambda is actually 2 here, and then 2, 2, and then 2. Yeah, I think that is right. So you have this as A, this is A, and then x, I mean this is A minus lambda I, then x equal to 0. Yeah, that is perfect. You need to solve for x. Can you do it? Yes, I think using row reduced echelon form we can quickly do it. So let me just go to the next page, and let me solve for the x. So if we apply the reduction, then you can directly see that this is 0. I mean, you can directly make them 0, right? Because after the subtraction. So let me make them 0. I mean, okay, if you want me to do step by step, I can do it. This is 2 2 2 2, and then this is 0 0, right? That's how we solve the system of linear equations. Now you make them at 0, then after the reduction you will be having 2 2 0 0 0 0, right? Now from here you can definitely say that this x2 is a free variable, right? So x2 is k, and x1 is, so 2x1 plus 2x2 equal to 0. So from here x1 equal to minus x2, so x1 is minus k. So you can say that the vector you are getting is x1 x2, x1 is minus k, and x2 is k. So you take k common, this is minus 1, and then this is 1. So this is the set of all eigenvectors that you have corresponding to this value, which is lambda equal to minus 1, right? So corresponding to lambda equal to minus 1, these are the set of all eigenvectors that you have. So for lambda equal to minus 1, these are the set of eigenvectors. Now my question is that how many eigenvectors are there corresponding to lambda equal to minus 1? Actually it's always infinite, right? So you will say it's infinite eigenvectors. Now if I ask you that, okay, that's infinite eigenvectors, that is okay, but how many of them are linearly independent? You will say just one. See, you will always be having a free variable here. That is for sure. Why? Because the determinant a minus lambda I itself is 0, right? That's how you calculated this lambda. Since this determinant is 0, it means that this rank is since this is the square matrix, and we always find the eigenvalues and eigenvectors for the square matrix. Okay, so this complete is square matrix. It means that there must be the free variables. I mean, there must be the linearly dependent columns actually, right? Because the determinant is 0. The way we have constructed this a minus lambda I, okay, this a minus lambda I, the way we have constructed, the way we have calculated the value of lambda itself is making this determinant 0. So you will always be having the free variable, which means your final eigenvector will always be having the free variable. It means there are always infinitely many eigenvectors corresponding to any lambda, right? And that is also logically true, that I told you, that corresponding to any lambda there are infinitely many eigenvectors. I hope you are connecting the dots, because if x is eigenvector, then kx is also eigenvector. So that is why I always get kx actually. Like I mean, after solving, you will never get just one eigenvector. You will always get infinitely many eigenvectors. You will always get at least one free variable corresponding to one lambda, right? Now, how many of these are linearly independent? Then you will say just one, right? So there are obviously infinitely many eigenvectors corresponding to lambda equal to minus 1, but just one linearly independent. Okay, let's not worry about linearly dependent, independent, these things. Let's just build the basics. Let's just first solve for lambda. Let's just first solve for x, and then we will be talking about all of these stuff, right? So let's calculate eigenvector for lambda equal to, what is the next value? 3. Okay, for lambda equal to 3. So you have here, it is, I think this is 1 minus lambda. Let me probably copy this. Okay, and lambda is 3. So that is why you will be having you will be having 3 here, which means this will be minus 2, and this will be also minus 2. Okay, good. Then like both of these are minus 2. This is minus 2, this is minus 2. You want to make it 0, you can, I think, add both of these rows, and then you will be getting, okay, see, this is not in the determinant. This is basically the matrix a minus lambda into x equal to 0. That's what you want to solve, right? x1, x2. Okay, so you can add both of this. This is minus 2 to 0 0, and then you will be having x2 equal to k, and x1 is minus 2x1 plus 2x2 equal to k, which means x1 equal to x2, right? So, and which is k. So basically you will be having final vector, which is x1 x2, which is just k. 1 1. How many are they? Infinitely many, right? There are always infinitely many. For any lambda, there are always infinitely many, because there is always a free variable. And why there is always a free variable? Because the determinant a minus lambda I is always 0, and I am solving for a minus lambda I into x equal to 0, and the determinant, this determinant is always 0. That is why I will always be having the free variable. Okay, I hope you understood. So that is how you can calculate the eigenvalues and eigenvectors. I hope that is fine to everyone. Now let's just do one more question for the sake of practice. So these are the answers. Okay, the eigenvectors are not written here, but yes, I think we calculated it. So corresponding to lambda equal to -1, if I remember correctly, it was 1 minus 1k, right? And corresponding to this, it was 1, 1, right? Let me just check it. Yeah, 1 minus 1 or minus 1, 1 does not matter. It's a constant difference. Like you can take minus k or k. So minus 1, 1 or 1 minus 1 does not matter. So yeah, if you want, you can write minus 1, 1 or 1 minus 1 does not matter. Okay, cool. Now let's solve the next question. Find the eigenvalues and eigenvectors for the following matrix. So what you need to do, you need to follow the same process and you need to find the eigenvalues and eigenvectors. Let me just show you the eigenvalues and then we can do the eigenvectors, right? So to find the eigenvalues, you find the determinant of this, which is 0. Now you can expand using just this column because this is having 2 rows. So maybe 2 zeros. So maybe you can just expand using just this column, which means 9 minus lambda into 1 minus lambda minus 0, right? Which means 9 minus lambda into 1 minus lambda into 3 minus lambda. So this will be 0. I mean, you can directly do it using this column, right? Using this column, you can directly expand. And from here, you got 3 lambdas. Now what you need to do, you need to solve for all of these 3 lambdas and then you need to solve for the eigenvectors. So you can do that as an homework. So what you need to do, you just plug in lambda equal to 9 here. Whatever matrix you get, okay, so you will be getting a minus lambda I, and then you need to solve for a minus lambda I into x equal to 0. You can just comment it out your answer, that what you are getting as an image, you can comment it out. What you're getting as lambda 1 equal to 9, what you're getting as lambda 2 equal to 3, what you're getting as lambda 3 equal to 1. Okay. So we will actually solve many other questions. That's why I'm not solving this question. It's not like that I don't want to solve. It's just that we will be solving many other questions. So I'm leaving this easy question as an homework. You can just try it out. Okay. Now let's see one very nice statement, which is very, very powerful also. What this statement is saying, that eigenvectors are different for like eigenvectors from the different eigenvalues are linearly independent. What do I mean by that? That if two eigenvalues are not equal, then the corresponding eigenvector, let's suppose here you have E1 eigenvector, here you have E2 eigenvector, then E1 and E2 are linearly independent. That's what this statement is saying. We can prove this easily, but for proving, at least you should understand that what this statement is saying. So what it is saying is that corresponding to lambda 1, let's suppose you have multiple, I mean obviously there will be multiple eigenvectors, right? Let's suppose this is 2 3, this is 1 2, let's suppose this is 4 6, this is again 2 4, something like this, right? So corresponding to lambda 1 there are multiple, let's suppose. Now similarly corresponding to lambda 2, again there are multiple, 3 5, okay, maybe let's suppose 2 9, let's suppose 6 10, anything, okay. Corresponding to lambda 1 there are multiple, corresponding to lambda 2 there are multiple. I'm not interested in the eigenvectors among the lambda 1, okay, because this question is saying that pick any eigenvector from here, which means pick any eigenvector which is let's suppose 2 3, and pick any eigenvector from here which is let's suppose 2 9. If lambda 1 and lambda 2 are not equal, then these two eigenvectors are linearly independent. You can pick any from here, you can pick any from there. That's what this theorem is saying, or the statement is saying. Okay, don't tell me that let's suppose you say that, sir, why this 1 2 and 2 4 are there, these are not linearly independent. No, I am not talking about within the same lambda. No, we are taking eigenvectors across two different lambdas. Okay, we are taking eigenvectors across two different lambdas. Let's suppose let me pick an eigenvector E1 here, let me pick an eigenvector E2 here. So these are the two different lambdas. I'm picking the eigenvectors from two different lambdas, and then I'm saying that E1 and E2 are always linearly independent if lambda 1 and lambda 2 are not equal. This is what this statement is saying. Is this a statement saying that if lambda 1 and lambda 2 are equal, then they are linearly dependent or something? No, right? I mean, this is just one way, which means if lambda 1 and lambda 2 are not equal, then the corresponding eigenvectors are linearly independent. That's what this statement is saying. Can we prove it? I think we can easily prove it. Okay, so let's just try proving it. I mean, proof is first of all optional. See, if the proof is not optional, we will tell you that you should be understanding the proof and it will help you in the gate. this proof that I'm going to spend just I think 2 minutes is actually optional, which means that it might not help you in the gate, to be honest. Okay, but the statement is important. But then why we are proving it? Maybe just for your curiosity, maybe just because you want to appear for the interview. That's why. Okay, I mean later you might want to appear for the interview. Okay, so it is given that lambda 1 and lambda 2 are not equal, and we want to prove, to be proved, that E1 and E2 are linearly independent, right? Okay, so let's see the proof. Let's suppose, for the sake of contradiction, okay, for contradiction, let's assume that E1 and E2 are linearly dependent actually, which means E1 equal to maybe KE2. I mean, I'm assuming that E1 equal to KE2, which means they are actually linearly dependent. But something will happen because it is a contradiction, and then we will show that okay, because of this, the contradiction, that whatever the assumption we have made, it is false. I mean, for the contradiction we are making this assumption, so this is assume, okay, assumption. Now if you assume this, then I think from here what we can do, see, let's just multiply a E1. E1 is eigenvector corresponding to lambda 1, so it will be lambda 1 E1, right? Now the other way to do this multiplication is that we just write, instead of E1 we just write KE2. First you write KE2 and then you multiply A and E2. It will be now lambda 2, okay, lambda 2 E2. See, it is given that E lambda 1 lambda 2 are eigenvalues and E1 E2 are corresponding eigenvectors. So that's why these two things are given actually, right? So A into E2 is lambda 2 E2. So K lambda 2 E2. So what we did, we just did this A1 into two different ways, directly with E1 or instead of E1, I'm rewriting it as E2 and then I'm doing. So I finally got that okay, A1 is this also and this also, which means these two should be same. So just to be on the same page, let me write this E1 also E2. So which means lambda 1 K E2, right? Lambda 1 K E2. See, it's just a trick that we are playing. We are writing this AE1 into two different ways. AE1 directly you multiply, you will be getting this, right? And then you rewrite this even after multiplication, which means after once you multiply A into E1, you rewrite this even as KE2. And another way to multiply is that you write this even as KE2 before multiplication, and then you multiply A into E2. Then you will be getting in terms of lambda 2. So basically, we just did A1 only, but in two different ways. So what? I mean, these two must be equal, right? Because these two are actually equal to A1. So these two must be equal to each other. So from these two equations, you can say that lambda 1 K E2 equal to lambda 2 K E2, yeah, right? And then you can just cancel out this K, right? And then from here you can say that lambda 1 E2 minus lambda 2 E2 equal to 0, and then you take E2 common, then lambda 1 minus lambda 2 into E2 equal to 0. And since E2 is an eigenvector, E2 cannot be 0. See, if the multiplication of two things are 0, I mean it is one vector, let's suppose multiplication of vector and the constant is 0, it must mean that either this constant is 0 or this vector is 0, right? Then only you can get the 0 vector. Right, that is the only meaning we can infer from this. But here, this vector cannot be 0 because of this E2. E2 is an eigenvector, it cannot be 0. So this constant must be 0, which means that lambda 1 minus lambda 2 must be 0, right? Which means from here you can say that lambda 1 minus lambda 2 must be 0. And then from here lambda 1 equal to lambda 2. But which is not possible because it is given that lambda 1 and lambda 2 are not equal. So this is false. So what went wrong? It means that our assumption went wrong, right? So that means that this cannot be true. The assumption that we have made, it is wrong, which means that E1 cannot be expressed as K into E2, which means E1 and E2 are not linearly dependent, which means they are linearly independent. So that's how you can prove it. See, this is just a trick that people have played to prove it. And there is no like intuition. I can say that you can have that. Okay, this is how you need to prove it. people just did it, which means that they just rewrote this even a1 into two different ways. First, using directly multiplication, then they are replacing even as ke2. Secondly, first they are multiplying these two. Okay, sorry. First they are rewriting this even as ke2, and then they are multiplying. In the first way, they are directly multiplying a even, and then they are rewriting even. In the second way, they are first rewriting even and then multiplying this ke2. I mean, that's the only difference. Anyway, I hope you understood it. If you have not understood, it's completely fine, and this is optional. See, sometimes if it is optional, then I will tell you that it is not at all useful, and I will actually also explain it fast, which means that in that case, if I know that it is not going to be very much useful for your gate, then maybe I will just explain this fast. Because see, useful in the sense, it will not even develop any intuition for you. Okay, which means that even if you know this proof, you will not be getting any intuition to solve any other question. So that is why, like, we just explain a few of the things fast. Okay, cool. I hope you understood this. So anyway, like, for our purpose, this statement is important. And then don't worry if you have not understood this, because we will make use of this statement many times, and I make sure that you understand this. Okay, so that's actually very, very useful, very nice statement. But it, like, using more questions, using more different type of variations, you will get to understand this. Okay, if there is any problem, you can just comment it out. But yeah, this statement is very, very important, so you cannot skip this. Which means, if two lambdas are not equal, then correspondingly eigenvectors are linearly independent. Okay, so see, in the previous example also, these lambdas are not equal. If you notice, these lambdas are not equal, then these eigenvectors, corresponding eigenvectors, are also linearly independent. You cannot get 1 1 from this minus 1 1, right? You cannot get it. The correspondingly eigenvectors are also linearly independent, because these lambdas are not equal. And this statement is actually very, very nice, very, very useful, very powerful statement. That's why we are having it. Okay, so thank you so much. Just remember this statement, skip the proof. Thank you.